Welcome to The Explainer. Today, we're going to pull back the curtain on a piece of engineering that you literally use every single day, but probably never see. It's what keeps your music sounding crisp and your data flowing cleanly. It's called the Butterworth Filter, and trust me, it's one of the true unsung heroes of our modern world. So let's start with a question. Have you ever wondered why your favorite song streaming through your headphones doesn't just sound like a wall of fuzzy static? The answer is all thanks to a concept called filtering, and more specifically, a brilliant design that's basically a bouncer for sound, deciding exactly what gets in and what gets kicked to the curb. So here's how we're going to break it all down. First, we'll tackle the problem of noise itself. Then we'll meet the basic solution, the low-pass filter. After that, we'll see what makes the Butterworth so special. That's the Butterworth advantage. Then we'll peek under the hood at its blueprint, and finally, we'll see how that plan becomes a real thing you can build. All right, first things first, we have to talk about the universal problem in all electronics, the unwanted guest at every single party: noise. It's the hiss in your audio, the glitches in your video stream, the fuzz on a medical scan, and it's the one thing engineers are always trying to get rid of. You know, you can think of any electronic signal as a conversation in a really crowded, loud room. The actual music or data you want, that's the voice you're trying to hear. Everything else, that random static, that low hum, that high-pitched hiss, it's all just background chatter. And this noise can totally ruin the conversation. The only way to fix it is with filtering. Okay, so let's get into the basic tool for fighting this noise. If noise is that annoying guest trying to crash the party, the low-pass filter, well, that's the bouncer at the front door. And its job is actually super simple. It lets low-frequency signals pass through, but it slams the door on high-frequency signals. This works because, a lot of the time, the good stuff, like the rich sounds and music, is in the lower frequencies. And all that annoying noise, like static, that's usually way up in the high frequencies. And you gotta understand, this simple concept is absolutely fundamental. By setting what's called a cutoff frequency, engineers basically draw a line in the sand. They're telling the circuit, look, anyone below this line is a VIP. Let them in. Anyone above it? Nope, they're not on the list. So you might be thinking, okay, if a basic filter does the job, why do we need a bunch of different types? Well, this is where it gets really interesting. This is where the genius of the Butterworth design comes in. See, it's not just about letting the right frequencies through. It's about how you treat them once they're inside the club. Because the ultimate goal here is perfect fidelity. You want the signal that comes out of the filter to be exactly the same as what went in, just, without all the junk. To do that, you need what engineers call a maximally flat response. Think of it as a perfectly clean, clear window, not one that adds some weird color or distortion. And this right here shows you exactly what I mean. That passband is just the range of frequencies the filter lets through. Now look on the left. A lot of other filters, they have these little ripples or bumps. It's like sending your audio signal down a bumpy road. It's going to get shaken up a bit. But the Butterworth filter, on the right, it's famous for being maximally flat. It's a perfectly smooth highway. The signal comes out completely untouched. So the big question is, how in the world do you build a filter that's so perfectly flat? Well, it doesn't just happen by luck. It takes a very, very precise mathematical recipe. A blueprint for perfection. Okay, at the very heart of this design is something called a transfer function. Now, don't let the technical name scare you. Just think of it as the filter's DNA. It's the unique genetic code that tells it exactly how to behave. You don't need to solve it, you just need to know it exists. And here is that genetic code in its raw mathematical form. I know, it looks a little intense, but we're going to ignore almost all of it. Just focus on one single letter in there, N. That's called the order of the filter. And you can just think of it as its power level. It's really simple. The higher the number N is, the sharper and more effective the filter gets. A low-order filter is like a gentle slope, kind of letting some noise slip by. But a high-order filter, that's a super steep cliff. It gets incredibly close to what engineers call a brick wall, a perfect, sharp separation between the good stuff and the bad stuff. Now, you might be thinking, do engineers have to solve that monster equation every single time? And the answer is, thankfully, no. They use tables just like this one. This is basically an engineer's cheat sheet. You need a fourth-order filter? You just go down to the row for n equals 4, and boom, it gives you the exact recipe you need. It's the perfect bridge from pure math to the real world. All right, enough with the theory. Let's see how this all comes together.
we're going to walk through a real-world example of an engineer taking that cheat sheet and turning it into an actual physical circuit that does a job.
And the process is really logical. It's as easy as 1, 2, 3. First, you figure out what you need. Second, you look up the instructions on the blueprint. And third, you just build the thing. So, step 1, define the goal. Let's imagine the boss comes over and says, hey, I need a low-pass filter. It's got to be 4th order, so we get a nice, sharp cutoff. And I need that cutoff to be right at 1 kilohertz. Okay, the mission is clear. Step 2, consult the blueprint. Easy enough. The engineer just pulls up that cheat sheet we saw a second ago, goes down to the n equals 4 line, and copies down this exact mathematical instruction. This is the recipe. But here's the really slick part. If you look closely at that recipe, you'll see it's actually 2 smaller chunks multiplied together. And that tells the engineer something amazing. They don't have to build one giant, complicated 4th-order circuit. They can just build 2 much simpler 2nd-order circuits and string them together, one after the other. It's called cascading. And what are these simple little circuits made of? Just basic, off-the-shelf electronic parts. You've got an amplifier, which is kind of the engine, and then a few resistors and capacitors. And the exact values you need for those parts are calculated directly from those numbers in the blueprint. And that's the whole magic trick, right there. You have this abstract, pure math formula, which gets turned into a simple cheat sheet, which gives an engineer the exact instructions they need to grab a few physical parts off a shelf, solder them together, and create a real-world circuit that gives us that perfect, clean, noise-free sound we expect. It's beautiful. So, to wrap it all up, we've been talking about sound, but this idea of filtering, of cleanly separating the signal from the noise, is absolutely everywhere. It's in your Wi-Fi, it's in medical imaging, it's even in the social media algorithms that decide what you see. So that leaves me with one final question for you. What other invisible filters are out there, quietly shaping the world you experience every single day?